This is Torrance doing with Lab 5 motion of falling objects. My first observation was to watch a wallet that dropped rapidly and then to drop a paper towel that dropped slowly. The main result that we're trying to prove here is that air resistance is going to cause them to fall differently based upon their mass ratio. Some other objectives we're trying to look for is to compare the falling velocity of the two different objects. With this, we can find the terminal velocity and the difference between our air friction to weight ratio. The first thing I did was record my two videos of a paper towel falling and a wallet falling, and then uploaded them in Tracker. The first video that we have here is the paper towel that's falling. Here I've set my axis, you can see, to when it falls. It just falls at this rate. So when I play it, you can see that my points that I found are right along that. The length of my video is about 0.25 seconds, and my length scale is about 0.05 meters. And then here was all the data that I gathered from this. Same thing with the wallet. If we just watch it fall, I set the origin to right here at the center of my object, so it would just fall. So there we go, and we can watch that. The time of this video was 0.417 seconds, and I set my length scale to 0.2 meters. The average location is just plotted along these lines with the gather that I dated right here. So once I've analyzed these in Tracker, I went to my VPython program, and this was my computational model that I used. The first thing I had to do was set the mass of my object. So for this instance, I used the mass of my wallet, which was about 0.50 grams, and then my ball position, I'm just using that vector as 0, 0, 0, and same thing with the velocity, since these are just starting at an initial time. My time was 0.417 seconds, which is what I had gathered in my Tracker data. Pretty much, this model is going to show like the gravitational force, which is equal to 9.81, and my f-grav vector is just 0. The negative ball that's falling over here in this program. So that shows that the ball. There's my ball velocity and my ball position. So once I run this program, you can see that it starts at an initial position and just falls. This graph just shows it falling rapidly. So once I gathered the data from that, I used an Excel sheet to compare the differences between my observations to my computational model. This one right here shows the paper towel. The blue line is from the model that I used, and I changed my mass in that model to represent the mass of the paper towel. Here you can see that this line just towards the end falls off to be a linear line, which it eventually reaches its terminal velocity. But as you can see, the line that I got from my Tracker, I didn't have as many data points due to the short length of the video of the paper towel falling slowly. But if this was to continue, I think that maybe it would slope a little bit more. So then I did the same exact thing with the wallet. The blue line represents the model data that I'd gathered in VPython, and here was mine. You can kind of see the difference. Same thing with the blue line, it falls off towards the end, and it eventually will reach its terminal velocity. If I gathered more data points of mine, I think mine would do the exact same. The blue line in this is very similar to the same line that I used for the paper towel. I just changed in Tracker, or in VPython, whenever I was running both the modules, I just changed my mass. The mass of my wallet was about 0.50 grams, and the mass of the paper towel was about 0.05. Moving on to part C, where we use the motion prediction of our object, where if our object was falling down, we needed to prove that
the drag force was moving in the opposite direction, which means that it would be going up. So when I go to my VPython code, to my initial conditions and my system properties for the mass of my object, I just set it to what my wallet was equal to, and my initial conditions, I just kept my vector all starting from an initial position like I had in Tracker along that axis, so I kept all my vectors as 0, 0, 0. I used my time step as 0.01. So here I'm just kind of like trying to prove that the net force is equal to 0, and that eventually the graph will reach its terminal velocity. So once I ran this in VPython and I got my information, I tried to prove what does this mean. So I used a certain model to imitate my drag force in this. So I had my paper towel dropping slowly and the wallet dropping at a rapid rate. So here you can see the paper towel that drops slowly versus the wallet that drops very quickly. With the drag force, the line just seems to like kind of flatten out, as you can see right here. This happens because the drag force is proportional to the velocity. It keeps increasing, so our net force is eventually going to equal 0. When these forces do equal each other, the pushes and pulls will also equal the same, and they will catch on to each other where our velocity will stay 0. This is stated by Newton's law also. So these are my graphs from the data I had gathered from VPython, where the paper towel was falling and the wallet was falling with the drags. So what if we had the wallet dropping slowly? I kind of used my models to examine the object's velocity as a function of time, and where the object was, like if the object was thrown downward initially instead of dropped from rest, how would that affect the graphs? I was going to test to see if it ever reached its terminal velocity with and without drag, and why it changed whenever, and how it differed from when it was dropped from rest and not. So if I, in VPython, I just used my code and I just set my initial velocity to -5, so it just proves that it wasn't starting from rest 0, as you can notice in all these. And you can just notice that it hits its terminal velocity much quicker than it would whenever it was just dropped from rest. The model without drag just keeps increasing in the velocity as it is shown here in these graphs. The velocity is the slope of the position line, so here we can see it with the paper towel with the drag and with no drag, and then on my wallet with the drag and without the drag. So basically from this lab, my chief results was that drag is related to terminal velocity, that velocity is very related to air resistance. My pushes and pulls did equal 0. Eventually all my graphs did taper off towards the end to reach its terminal velocity, and that our drag force is opposite to the force of gravity in free fall.